Last week we managed to do everything which I really wanted to do in this course, kind of the core material. In particular, this beautiful result of the analytic semigroups, where we have to do these fancy path integrations. And then one point is within the loop, the other point is not in the loop. And we might remember this. So this is really something I wanted to show. Now, for the rest of the course, I call this supplemental material. So this is kind of designed to, if we have time, we do it. And if we don't have time, we don't do it. Not so essential. These are 3 little results. And I thought maybe I just present the results and tell them what they mean, but not do the proofs in detail. The proofs are written out here in the manuscript, so you can see them anyways. But maybe I just take it easy for this lecture, talk about the theorems, and then at the end give you a good summary of the semigroup stuff. So here, the first result, theorem 8.9.1. If A generates an analytic semigroup e to the at, then there are constants c and omega so that A e to the at is bounded by c e to the omega t divided by t. This is a technical estimate, but it also tells you what happens if you apply A to the semigroup. And important here is the 1 over t dependence, which you see right here. Okay, so this tells you that this estimate for t close to 0 is basically useless. So this kind of regularity only kicks in if t is a little bit away from 0. And this is something we will see later, where we also have to assume that the time is a little bit advanced. So meaning the initial condition might not actually satisfy this, but then after we move on, we get a good estimate of A applied to e to the at. So this already goes in direction of regularity, and I tell you more about this in a second. The proof uses this path integration stuff, right? And then does a whole bunch of manipulations. You're probably not surprised to see these kind of arguments. Okay. The next result, which is of some importance, is again a perturbation result. And it turns out semigroups can be perturbed by operators which are dominated by the semigroup. We had this in general, an earlier result where we have a general semigroup perturbed by a bounded operator. Now we have an analytic semigroup, and the perturbation can be an operator that is bounded by A. So in fact we need B is a perturbation, minus some integer number B. Identity is bounded by the operator A with a constant little a. But then this can't be any little a, this must be a little a which is bounded by 1 plus m epsilon to the minus 1. And m epsilon was this estimate which we had from the definition of a sectorial operator. You might remember in sectorial operators we had a sector which is less than sigma pi over 2 plus delta minus epsilon for a little epsilon, and on this a little bit smaller sector we had a uniform estimate where showed up this m epsilon. So this goes back to the very definition of sectorial operators with this m epsilon. But if we have it, then we know what A can be maximal, and then AX must dominate BX, or in this case B minus little bx. And then the combination A plus B is also generator, but also generator of an analytic semigroup even. Okay, so I call this perturbation by operators which are dominated by A. So then here is a proof. So you see that these sectors appear explicitly in the proof, where you then get also use of this m epsilon from the definition of a sectorial operator. Next page. And we do all kind of tricks with the resolvents and so on. And at some point you show that the resolvent set of A is included in the resolvent set of A plus B. And you remember the sectorial operator, the sector defines a subset of the resolvent set. And so if the sector is in row of A, then the same sector is in row of A plus B. So this makes A plus B sectorial as well. And then we can show it has the same estimate. And then the last one is the regularity result for mild solutions. You remember mild solutions were defined through the variation of constant formula. I didn't write it down here because we had it earlier already. Okay, and then we show a proposition, which I even skip here. Come on. Here's the result. So we look at f in C0 theta, so Hölder space, Hölder continuous functions, f, and the differential equation we are looking at is u dot is au plus f of t, okay, and f is Hölder continuous. And then what we can basically show is that au and u dot are also Hölder continuous. So this guy is C0 theta, so then we can show that this is C0 theta and C0 theta. However, with a few restrictions. So let's look at number 1 first. So the mild solution is C0 theta after some initial time delta. And this goes back to the estimate I've shown you in the beginning of this video, where you have a 1 over t dependence, right? So if t goes to 0, it goes through the roof. So we need to advance a little bit, a little increment, time increment delta, and then we have the estimate desired. Unless, if the initial condition is in a domain of definition, then we can actually go down to t is 0. Because then the initial condition is already smooth in that sense, and we do not need the initial time delta. However, you see here I only in C0 and not C0 theta. If I want the Hölder continuity, like in number 3, I need in addition u of 0 is 0 and f at 0 is also 0. So then this is the best result, so we have the theta there and we have the time 0 there. So this looks like a very detailed proof where you have to look very much at the details. If time is 0, what is the initial condition, what do the functions do at 0. Essential here though is the regularity, right? So A often is, you should always think about the Laplacian, the second derivative. And so if the second derivative is C0 theta, that means the function is C2 theta, right? So it's twice differentiable with the Hölder continuous derivative. And this is called regularity. So this means the function is very smooth, much smoother than we might have expected. Similar for the time dependence up here, right? So now the time derivative is C0 theta. This means the function is continuously differentiable in time. So in particular, these are classical solutions, right? So that's the entire idea of regularity. Here again, I give you an example of Hölder spaces. You can do this with Sobolev spaces, with higher order Sobolev spaces, and so on. So there's a whole theory of regularity. And there's a beautiful book by Alessandra Lunardi, which is a thick book, and it's only about regularity of semigroups. It's a research area in its own rights, and if you find this interesting, you might check it out.